One more example, actually, but a slightly different one to illustrate something that we will use later on in the course also. An example, suddenly, where the binomial distribution pops up again, even though we were on a day doing continuous stuff. Let us have a look at this example. I'm going to do it a little bit rapidly, then you can read about it in the book. Here is an experiment with 80 rats. It's assumed that the probability that a rat survives the experiment is 0.5. Do you believe that? I mean, the probability that an animal survives an animal experiment is 0. But, okay, until at least up to a certain point when we are not going to use it anymore, then we would, before we dispose them, it may be positive. Sorry about that, but that's how it is when Novo Nordisk and others do rat experiments. Any members of Anima or any? Don't throw at me with anything. My daughter wanted to be a member of Anima, but we had a discussion about that. I won the discussion, but maybe it'll fall back on me in 10 years or something like that. We'll see about that. Now she is a member of Dyrenes Beskyttelse. Dyrenes Beskyttelse, which is the Danish organization for protecting animals, is in principle against doing animal experiments, in case we could live without them. So they work for that we should try to move research forward such that one day in the future we can avoid making animal experiments. Until we can still save human beings from dying from cancer and other things by doing experiments on rats, we think it's a good idea. I agree with Dyrenes Beskyttelse. You may disagree, of course. It's a free country. What is the probability that at most 30 rats die in the experiment? What is the probability that at most, if X is the number of rats dying, I don't write everything now, X is the number of rats dying among the 80 rats, it's like a coin tossing experiment, 80 times, 50% chance of dying. Risk, we could call it. At most, 30 rats would die. That would be a binomial probability that, of course, we could find using Binomial easily. So you could say it's a bit old-fashioned rule that I'm giving you, but it has a meaning, the idea of it. The thing is, before we had the computer, people also wanted to compute things like this. And doing a binomial with 30, I mean, out of 80 and doing 31 computations of individual binomial probabilities and then adding them up, that was tedious 50 years ago, before we had the computers. The thing is, we can approximate such a probability by the normal distribution, at least in some cases. Let me try to illustrate it. Here we would have part of the histogram of the binomial with averaging 40. That's the mean of this binomial. So it will top up here and then it will go down again. Here I have, let me say, I would have 30, 29, 28. What I would like is actually all of these 30, 29, 28, 27, blah, blah, blah. All of them, all of these binomial probabilities I'd like to add up to get this probability. The idea is that if we put in a normal here, we can approximate this by taking the similar normal area. So actually, we would take a normal distribution that matches the binomial. How can a normal distribution match a binomial? If we choose it with the right mean and the right variance, we should use the mean and the variance coming from the binomial and then take the best possible normal, and then we can use it as an approximation tool. Actually, there's a little technical thing called a continuity correction. You can read about it also in the book. That's just a little thing that says, actually, if I'm going to use a normal distribution here, I don't want to take it in 30. Look at this. I want to include this bar here from the binomial probabilities. Now, if I cut off in 30, I would cut off the bar in the middle. And I would lack actually half of one of the bars in my computation. This is just a small technical thing called a continuity correction. So instead of using 30, I'll use 30.5. I'd go half, take this half correction. So I'll take this and I'll do an approximative calculation saying that this is the same as, should call it something else, y being less than 30.5. The 0.5 was the continuity correction. And what is the y here? The y would be a normal. Which normal? The normal using the binomial mean and the binomial variance. Right? I compute the mean and the variance as it looks for the binomial. I use it in the normal. Nice. And then we could go on and we could standardize this, and that would be the same as taking 30.5 minus the mean, NP, that would be 40 in this case. NP times 1 minus P, that's 20. We divide by 20 is the variance, so the standard deviation is square root 20. And then we compute this number, minus 2.12. Minus 2.12. Let's finish off. Did I have it prepared? We could also say P norm minus 2.12. 1.7%. I could also say P norm to 30.5 using what I've just showed you, the right mean and the right standard deviation. There is a rounding thing here with the 2.12, right? So it's still 0.17%. What would the exact binomial be? Also around the same thing. So I admit to you, being able to do this binomial computation sort of makes this rule a bit, as such, in itself, meaningless. I mean, why would I ever use this rule? And so it's just to say to you, in that sense, the rule itself may be old-fashioned, and yes, it is. It was called the Moivre-Laplace formula from the guys who found out about it many years ago. So quite astonishing. I wonder what's going on here. But the reason for me still showing it to you is that we are going to use the normal distribution in a much more substantial way in the future, in the rest of the course, because the normal has this very central property that it can approximate many other distributions. Basically any other distribution. For instance, the binomial. This was just showing you this explicitly. I wonder if I'm having a problem here. Do we have sound everywhere through? So it's just some local thing on my computer here, hopefully. I'll skip the B part here. So that's the similar thing. You can also do similar approximations to probabilities that look like this by going to the classical one, saying this is the same as subtracting from less than 42 the probability of being less than or equal 37, for instance. So, and then we could use the same thing over again. I'll not do it now. This would finish this example, so we jump to the next.